Okay, so today we are going ahead and we're starting with the topic of electricity. So the first thing we have to go over is the topic of electrical quantities. So when we talk about electrical quantities, let's go ahead. So we're going to be talking about charge, we're going to be talking about current, we're going to be talking about voltage, power, and all of those things, right? So when we talk about electrical charge, what is electrical charge? When talk about any charged particles, whether it's a negative particle or it's a positive particle, they carry a certain charge. Fine. Now, when we talk about charge, charge can be is measured in coulombs. That's the unit for it. You use the charge of you use the unit of coulombs. Now, one thing that you have to know at this level, what is the charge on a single electron? The charge on a single electron is minus 1.6 into 10 raised to power negative 19 coulomb. This value will be given to you in the exams, the data sheet. They give you the value, so you don't have to. So it's not necessary, but the value is used so often that if you learn it, it will just make your calculations easier because this value of charge of electron quite commonly, right? So because the value of charge of electron is used quite commonly, if you learn it, it will just make your calculations faster. So electron would, for example, have minus 1.6 into 10 raised to power negative 19. A proton would have positive 1.6 into 10 raised to power negative 19. Now, oftentimes you're going to see questions where they're going to ask you stuff like, what is the total charge? Fine. So the way you find out total charge is you use the formula Q is equals to N, where N is the number of electrons, right? So you have any material, you have any piece of metal. If you can count the number of electrons, or if the number of electrons are given to you, you can multiply them by the charge of one electron to calculate the total charge on any object or the total charge on any material. You can go ahead and calculate it, right? So this is the formula you guys can use. Q is equals to NE. Now, when we go ahead and talk about it, you guys know that we have two types of current, right? We have the actual direction of the current and we have conventional current. The actual direction of the current, we know now that electrical current is the flow of electrons. Fine. So whatever happens, what happens is that you have a charged particle, you have electrons. When those electrons experience a force, the electrons will move from the negative terminal to the positive terminal. The movement of electrons is known as electrical current. So because the electrical current is the movement of electrons, we know they've moved from the negative terminal to the positive terminal. That's the actual information that we have, that the charge flows from negative to positive. But conventional current, so before it was discovered that the electrical current is actually the flow of electrons, scientists used to believe that the current was positive charges. So they thought that the electrical current was from positive to negative. This is known as conventional current. Now we know better. We know that it's not the positive charges, it's the negative charges that are moving. So we know it's from negative to positive. But still these days, conventional current is considered to be from positive to negative. So electrical current is the movement of a charged particle when it experiences a force. And when you talk about it, this is the formula of current. Current is equals to charge divided by total time taken. The current is measured in amperes. So I is equals to Q upon T. Then we have voltage. Now, you guys must have heard different terminologies for voltage, right? Electromotive force, potential difference, voltage, all of these different terms. So what is the difference between them? What is EMF? What is potential difference? What is voltage? So voltage, if you define simply, right? Voltage is the amount of energy that is being transferred per unit charge. So on one charge, in moving one charge, how much energy am I transferring? Fine, that is simply defined as voltage. How much energy is being transferred per unit charge? The formula is simple. You calculate energy or work done and you divide it by the total charge. Whatever the total charge is, the energy being transferred or the work being done divided by the total charge, it should give you the voltage. Now, what about electromotive force and potential difference? Both of these are alternate terms for voltage, both of them. Electromotive force is the terminology we use when we talk about a battery. So whenever I'm talking about the voltage of a battery, I will use the term electromotive force. And whenever I'm talking about a load, like a lamp, like a resistor, I will use the term potential difference. And there's a slight difference in definition as well, right? Electromotive force is the energy transferred per unit charge, pretty much the same definition. Potential difference is the work done per unit charge. So that is a slight difference in definition. Work done per unit charge is going to be your potential difference. And EMF is the energy supplied, energy transferred or energy supplied per unit charge. Fine. So pretty much they're all the same thing. The differences between them are minute. They're not that different. The differences between them are minute. Fine. And when we go ahead and we talk about it, both of them are voltage. The concept of both of them is the same. You're dividing energy or work done by charge. And EMF is what we use when we talk about energy being supplied like a battery, while potential difference is normally used for a load like a resistor, like a lamp, or like any other functioning device. Now, we have something known as the electron volt. What is the electron volt? So electron volt is a unit, right? It's a unit in which basically what you do is that you take your, it's a unit for measuring energy. Fine. So what will I do? I have to do conversions. So 1 electron volt is equals to 1.6 into 10 raised to power negative 19 joules. 1 electron volts, right? So what I will do is if my voltage is given to me, and they say, can you convert it into electron volts? What will you do? You will simply multiply it by 1.6 into 10 raised to power negative 19. So 1 electron volt is equals to 1.6 into 10 raised to power negative 19 joules. So when you guys are doing past paper questions, you guys have to be really, really careful about this, because oftentimes they will ask you to calculate energy, but they will ask you to calculate it in electron volts. So you will have to multiply the answer. So you will have to go ahead and do the conversion, right? So they will give you, you will calculate the answer in joules, and then you will have to go ahead and you will have to change it into what? You will have to change it into electron volts. So always when you guys are doing past paper questions, be very careful. They do this quite often, that they will ask you to give the answer in electron volts, or they will give you the, you do the calculations in electron volts and they ask the question answer in joules. So you guys always have to remember to be very careful in the question and do the conversion properly at the end. Now, let's go over Ohm's law. Ohm's law is something I'm sure you guys already have an idea of. Ohm's law basically states that current and potential difference are going to be directly proportional to each other, provided that resistance and temperature remains the same. So if temperature is remaining the same and resistance is remaining the same, the current and potential difference should be directly proportional to each other. And how can you tell? By looking at the graph, you can observe a straight line going through the origin, meaning that it's a directly proportional relationship. When we talk about the formula, we know the formula is V is equals to IR, right? That's the formula. Formula is equals to V is equals to IR. Voltage is directly proportional to current, provided that the resistance remains constant. Now, this is the same thing you can observe in the graph over here. Now, when you talk about graphs, look over here. The current is on the y-axis and potential difference is on the x-axis. The axis can be labeled in different ways. You will see graphs where the current is on the x-axis and the potential difference is on the y-axis. Fine. So if a graph has been given to you where current is on the x-axis and voltage is on the y-axis, in those situations, you can directly find out the gradient of the graph, and that will be equal to the resistance. Fine. That's why whenever you guys are looking at these graphs, make sure you pay attention. If current is on the x-axis and voltage is on the y-axis, you can find the gradient of the line, and that will be equal to resistance. If voltage is on the x-axis instead of current, voltage is on the x-axis, in that situation, you will first find the gradient of the line, and then you will reciprocate it to find out the resistance. So you can calculate the resistance from the graph. Just be very careful as to what is on the y-axis and the x-axis. If the current is on the x-axis, directly calculate the gradient and it's going to be equal to resistance. If voltage is on the x-axis, then you will have to reciprocate the gradient. You will have to do 1 upon gradient, and that will be equal to your resistance. So any conductor, any resistor that follows Ohm's law, we call it an ohmic resistor or a ohmic conductor or a fixed resistor. Fine. So any conductor that is following Ohm's law, we call it a fixed resistor. Now, we have fixed resistors and then we have variable resistors. You guys need to know about 4 variable resistor: the filament lamp, the diode, the LDR, and the thermistor, right? Let's start off with the filament bulb. Let's take, first thing we have to understand is this graph that has been given to us, right? So when I take a look at the graph, first thing we will notice is that potential difference is on the x-axis, meaning that over here, the gradient is 1 upon G is equals to R. Fine, meaning that resistance and gradient have an inverse relationship. Now, what are we going to observe over here? What you're going to observe is initially the gradient of the line is high because you have like a steep slope, right? So initially the gradient of the line is high. But as you go on, as the potential difference keeps on increasing, the gradient of the line is also decreasing. So for example, if I take a look at the gradient over here, and I take a look at the gradient over here, because we make a tangent for the gradient, right? Whenever we have a curve. So you guys can see over here, the tangent is steep, meaning that initially the gradient is high. After that, the gradient is decreasing because the tangent is becoming more horizontal. We know that gradient and resistance have an inverse relationship. So initially the gradient is high, meaning that resistance is low. After a while, the gradient is decreasing, meaning that resistance is increasing. When I take a look at it, so that's what we're observing, that initially the resistance was low, but as the potential difference continued to increase, the resistance increased as well. Why are we observing this? Why are we observing this particular relationship? The reason why is this not a directly proportional relationship? Why are we getting this change in resistance? Why is the resistance changing? Why is the resistance not staying constant? The reason for that is because to understand this, we need to understand what is resistance. Fine. So generally, when you talk about a conductor, what is a conductor? A conductor is a piece of metal. Fine. What is metal? Metal has metallic bonding inside of it, which is what? A positive ion surrounded by a sea of delocalized electrons. And metallic bonding is the electrostatic force of attraction between the positive ions and the negative electrons. When you talk about it, it is the delocalized electrons that are moving from the positive terminal to the negative terminal. From the negative terminal to the positive terminal. Right? The electrons are flowing from the negative terminal to the positive terminal, and that flow of electrons is generating the electrical current. Now, what happens is this, that the electrons, as they're going to be going from the negative to the positive, they are going to be colliding with each other. These collisions are what leads to resistance. When the collisions are going to be less, the electrons are going to be moving faster. When they're going to be moving faster, you are going to observe what? You're going to go ahead and you're going to observe that the resistance is going to be lower, the current is going to be high because the electrons are moving without any impedance, without any collision slowing them down. What happens when this number of collisions increase? When the number of collisions increase, the electrons will be losing more energy because they'll be colliding with each other. They will be losing more energy and they are going to be losing more energy, and as a result they're going to slow down. When they're going to slow down, what is going to end up happening? That is going to cause a decrease in the electrical current because the electrons have because the rate of flow of electrons has decreased. So when we talk about a filament bulb, in a filament bulb, as the voltage continues to increase, what happens? Current increases. Increase in current does what? Increase in current causes an increase in temperature. It causes an increase in temperature, and the increase in temperature increases the kinetic energy of the electrons. Increases the kinetic energy of the electron. The electrons will start to collide with each other and they will start to collide with the positive ions. That causes the electrons to lose energy. They slow down, and as they slow down, the current decreases and resistance increases. So that is exactly what it is. Okay, that is exactly what is happening over here. So that is what's happening in a filament bulb. That's why you're observing this particular relationship, that as resistance is, initially the gradient is high, so resistance is low. Then as the gradient is decreasing, resistance is increasing. Why are we observing this change in resistance? Because of the heating up of the lamp, because of changes in kinetic energy, and as a result, collisions and loss of energy in those collisions. So this is what is happening inside a filament bulb. Any confusion? Does anybody want to ask anything? Okay. If there are no confusions in this, let's go ahead and talk about a diode. Fine. So when we talk about a diode, what is a diode? A diode is a material that only allows the electrical current to travel in one direction. Fine, meaning that when we especially talk about an alternating voltage, we know in an alternating voltage that the current is going in the forward direction and the current is going in the backward direction as well. It's going forward and it's going in the backwards direction. So in those situations, when we use a diode will only allow the current to go in the forward direction. It will not allow the current to travel in a backwards direction. This is the symbol for a diode, and the direction of the arrow shows you which direction of current it will allow to pass through. When we go ahead and we talk about a diode is made of a special material known as a semiconductor. Right? A semiconductor is a material that conducts electricity to a certain extent. It is not as good of a conductor as a metal, but it's also not an insulator. It's somewhere in the middle. Just give me 2-3 minutes. Okay, guys, just give me 2-3 minutes. Okay, so a diode is made of a material known as a semiconductor. So when we talk about a semiconductor, like I said, a semiconductor is able to conduct electricity up to a certain amount. And when you talk about a semiconductor, for example, silicon is a semiconductor. So these diodes are made of these special materials. And hold on, let me see if I yeah, we are going to talk about it. I will also explain to you guys why is it that a semiconductor is able to conduct electricity partially, right? What is the difference between an insulator, a metal, and a semiconductor? I will go over that with you. So a diode is made of a semiconductor and it only allows the current to travel in one direction. So that is exactly what you guys are going to observe in this particular graph, right? What are you guys going to observe? You're going to see that initially when the voltage is negative, you will see that the current is zero. The moment your voltage is going to turn positive, there's a rapid increase in the current. This is how the graph for a diode is going to look. So there's a certain threshold voltage, a certain requirement, right? A certain threshold voltage. As soon as the diode is going to meet that particular requirement, it's going to meet that threshold voltage, the current will increase. So this threshold voltage is like the minimum requirement. But generally speaking, the current is only going to be transmitted in one particular direction, that's going to be positive direction. Now, after that, we also have to talk about a thermistor and we have to talk about our LDR. When we talk about a thermistor, so when we talk about a thermistor, in a thermistor, we have to remember that a thermistor is used generally as a transducer or a sensory device, right? That is one of the functions of it. We can use it as a sensory device. And when we talk about a thermistor measures the changes in temperature, and as a result, it gives you an electrical output. So it's taking the input is temperature, changes in temperature, and it gives you an electrical output. The electrical output, when you talk about it, so what happens that there's an inverse relationship. Increase in temperature leads to decrease in resistance, and increase in temperature leads to increased temperature leads to low resistance, and decrease in temperature leads to high resistance. So it's an inverse relationship. The graph for thermistor also has a sigmoid shape. It looks like this, right? When you're going to talk about it, what is going to happen? That as your you will see that initially your gradient is low, meaning that resistance is high, and afterwards the gradient is increasing, meaning that resistance is decreasing. And that corresponds with what I just said. Initially, when the voltage is low, the temperature will be low, right? Low voltage means low current means low temperature. So when the temperature is low, the resistance is high because the gradient is low, right? Low temperature, low gradient, so the resistance is high. After that, what are we observing? We are observing that as current will increase, the temperature will increase. Increase in temperature will lead to a rise in resistance. And that is what we can, increase in temperature leads to a decrease in resistance. That's what you're observing over here. If I draw this for you, excuse how bad my drawing is. So initially the current is low. If the current is low, that means the temperature is low. So if the temperature is low, the gradient is low, resistance is high, inverse relationship. After that, as the current increases, the temperature also increases. As the temperature increases, the gradient is increasing, meaning that the resistance is decreasing. So again, it's showing you an inverse relationship. And this is the shape of the graph for the thermistor. Thermistor again is made from semiconductor materials, right? Then when we talk about light dependent resistor is again, it acts like a transducer, it acts like a sensor, right? The input it gets is light input and it turns it into electrical output, that is being changes in resistance. So when we talk about it, it also has an inverse relationship. Increase in light intensity causes a decrease in resistance. A decrease in light intensity causes an increase in resistance. That is the relationship, and the graph for an LDR is similar to this. Same shape you will observe for an LDR as well. So the shape of the graph for both a thermistor and an LDR is going to be the same. And when we talk about a thermistor can be used in a lot of things. For example, a fire alarm, when you talk about your ovens, microwaves, they all involve thermistors. And a light dependent resistor is often used in burglar alarms and light sensing devices, stuff like that. Now we have to go ahead and talk about something known as resistivity. What is resistivity? Resistivity is the property of a material. What do I mean by that terminology? What I mean by that terminology is that resistivity is the property of a material, meaning that it is this value, this resistivity. It is specific to the metal, meaning that each metal is going to have a specific value of resistivity. And as long as the metal you're using is the same, the resistivity will also remain the same. What is resistivity? So why is resistivity depending upon the material? Because resistivity depends upon how many electrons does that particular metal have. What is the shape? What is the size? Sorry, I'm when I say shape and size, I don't mean shape and size. What I mean is the number of electrons, charge density, the properties of that particular metal, right? So if one metal has a greater number of electrons, it would perhaps give you a different value of resistivity, while another metal with lesser number of electrons will give you a different value. So resistance is depending upon resistivity depends upon the material. It does not depend upon the shape of the material or size of the material or anything like that. Doesn't matter what length, what area, what dimensions you're using. As long as the metal is the same, the resistivity will also be the same, right? When we go ahead and we talk about our resistance, now resistance depends upon, first of all, what material I'm using. That is really important. The material that I'm using is going to affect my resistance. Secondly, what is the length? And thirdly, what is the cross-sectional area? This is the formula for resistance that you guys can use. Resistance is equals to resistivity multiplied by length divided by cross-sectional area. Resistivity, the unit for resistivity is ohm meters. Okay, so ohm meter is the unit for resistivity. And when we talk about it, we multiply it by length and we divide it by the area. That should give me the total resistance of any material, any sample, any resistor, anything that I have. Resistivity, though, is a property of a material of that particular metal. So resistivity is going to be different for different metals. So now, remember when we talked about our electrons, right? When I explained to you guys about our resistance, about how resistance is the collision of the electrons. Now, when we talked about this, I explained to you guys about the electrons and I talked about the speed of the electrons, that when the electrons collide, they tend to slow down and all of this. So generally what happens? What is all of this happening? So what happens is that whenever we apply a potential difference, whenever I apply potential difference along a piece of metal, one end will become negative, the other end will become positive. There will be an electrical field, right? Because one end is negative, the other end is positive. There will be an electrical field. This electrical field will cause what? From the negative side, the electrons will be repelled. So they will be repelled from the negative terminal. At the same time, the electrons will move towards the positive terminal because negative is attracted to positive. As a result, the electrons will move from the negative end towards the positive end. This movement of electrons, this slow movement of electrons is known as drift velocity. The movement of electrons, the speed of electrons as they move through a metal is known as drift velocity. And this drift velocity is very important because we use it in the transport equation. What is the transport equation? The transport equation allows us to calculate the charge. Sorry, I'm saying charge, I meant current. It allows us to calculate the current. We are now going to take a look at a new formula for current. The formula is this. Current is equals to NAVE. What is N? N is known as charge density. Charge density meaning the number of electrons, right? The number of electrons that you have per cubic meter. So in 1 meter cube, how many electrons do I have? That is known as charge density, and that is shown as N. So N is the number of electrons per meter cube. Then A is the area, very simple, cross-sectional area. V is the drift velocity, and E is the charge of an electron. What is the charge of an electron? Minus 1.86, minus 1.6 into 10 raised to power negative 19 coulombs, right? We discussed this at the start. That is the charge of one electron. So the charge of an electron multiplied by velocity, multiplied by area, multiplied by charge density, that is basically going to be what? That's going to be the number of electrons per cubic meter that is equal to current. This is known as transport equation, and it allows us to measure the current simply by taking a look at the electrons. So when we go ahead and we talk about it, what is the derivation or how are we deriving the equation? The way we're deriving the equation is quite simple. We know that current is equals to charge divided by time, right? Current is equals to charge upon time. Now, whenever we talk about a metal wire is cylinder in shape, right? So we need to calculate, first of all, when we take a look into it, if we can calculate the charge, if we can calculate how much charge is flowing through the metal wire, I can calculate the current. So I need to calculate the charge. Now, if you remember, I told you that when you take a look into it, we have N. What is N? N is the number of electrons per cubic meter or per meter cube, right? So in 1 meter cube, we have N number of electrons. And we can calculate the area. We can calculate the cross-sectional area of the wire. So when we go ahead and we talk about it, we have to calculate the total charge. What is total charge? Total charge, if you guys remember, I told you the formula right at the start. The formula I told you guys was Q is equals to NE. Fine. So when we go ahead and we take a look at this, N is the number of electrons in 1 meter cube. The total volume of the wire we can calculate, right? Whatever is the total volume of the wire. So N is the number of electrons in 1 meter cube. And if we multiply it by the total volume of the wire, we can find out the total number of electrons. And if we multiply that by E, what is E? The charge. So we should be able to find out our Q. Fine. Now, let's break this down further. We know volume is equals to area. We know volume is equals to area. Oh, sorry. We know volume is equals to area multiplied by length, right? If I find out the cross-sectional area and I multiply it by the length of the cylinder, I can find out the volume. So we know that Q is equals to NE. The number of electrons, we know how many electrons are in 1 meter cube. So we multiply it by the total volume. So that should give me the total number of electrons. Now, I know that volume is equals to area multiplied by length of the cylinder. Fine. Now, so that means I can substitute, instead of writing down volume, I can write down area multiplied by length. So my total charge is Q is equals to NaL multiplied by E. Now, we know current is equals to charge divided by time. So NaLe divided by time. Now, we know length divided by time is equals to velocity. This distance divided by time or length divided by time is equals to velocity, right? The length of the cylinder is the distance covered by the electrons. So distance or length divided by time is equals to velocity. So length upon t can be replaced by velocity. So our equation becomes NaVe. And this is our transport equation. Is this clear now? Is this making sense to you guys?
Yes, miss.
Basit, is this making sense?
Yes, ma'am.
So that is how you guys are going to be doing the calculations. Now let's talk about our semiconductors, right? When we talk about a semiconductor, so I told you guys a semiconductor is only able to partially conduct electricity. Now, what is the reason behind it? Why is it that semiconductors are only able to partially conduct electricity? The reason for that is that semiconductors only have a small number of delocalized electrons that are free to conduct, right? They only have a small number of delocalized electrons. So the number of delocalized electrons found in semiconductors are not as much, or you cannot compare them to the number of delocalized electrons you can find in metal. Now, to understand this concept, we have to think a little bit back to the topic of waves. When we did the topic of waves, I told you guys about energy levels. Remember? We talked about the electrons jumping from one energy level to another, and we talked about how they need to have that specific energy to go from one level to another. If they have that specific energy, they will be able to jump to a higher energy level. If they do not have the specific energy, they will not be able to move. So when we go ahead and talk about it, when we talk about in a solid material. So in solid materials, where you have a lot of atoms that are really close together. So when you have a solid material and so many atoms are jam-packed, they're all packed close to each other, what happens? That the energy levels tend to, combine together. The energy levels tend to combine together, and they tend to form these energy bands. So when you talk about it, what is the energy band? So energy band has got multiple energy level inside of it. So an electron, for example, can be in the same energy band, but it can have a range of energies. So energy level is a very specific value. That it's 2.8 joules, it's 2.8 joules. You're at that very, very specific value, right? When we talk about our solid material. So in solid materials, when you have a lot of atoms that are really close together, these energy levels will group together. And when they will group together, they will make an energy band. So in that energy band, multiple energy levels have been grouped. So you're going to have a range of energy levels, not a specific value. You can have a range. So for example, an electron can be 2.8, 3, 4, 5, and it can be in the same energy band. It's still at different levels. Don't confuse that. The levels will still be different, but since the levels are in the same energy band, so the electron can have a range of energy and still exist within the same band. And when you talk about it, the area between these bands, the difference between these bands, for example, this, right? The area between these bands, this is known as the forbidden zone. So the electrons cannot exist in the forbidden zone. They can either be in one energy band or they can be in another energy band. They cannot exist within the forbidden zone, right? So when you go ahead and talk about it, um, we have two energy bands that you need to know about. We have the valence band and we have the conduction band. Fine. So when you talk about it, what is a valence band? A valence band is the electrons that are found in the valence band are still tied to the atoms. They're not delocalized. They're not free. They're still attracted towards the electrons, and they, since they're not delocalized, they cannot actually contribute to the electrical current. Those electrons that are found in the conduction band, they're able to delocalize, they're able to become delocalized, and they can move through the material and cause the movement of electrical conduction. When we talk about a metal, so in a metal, you guys can see this is the valence band and this is our conduction band. The space between the valence band and the conduction band is practically very small. It's practically non-existent. So electrons need to only give a little bit of energy before they can jump from the valence band to a conduction band, and they can also, they can actually, become delocalized. Another thing you will notice is that the conduction band is full, almost full in metals. The conduction band is almost full, so the electrons are repelled with each other, so it's easy for them to become delocalized. When we talk about a semiconductor, the gap between the valence band and the gap between the conduction band is wider. It is wider. It is not as wide as an insulator. The gap in the conduction band and the valence band in an insulator is really high. Because it's really high, the electrons need a huge amount of energy to overcome the forbidden zone, the forbidden gap, and actually move from the valence band to the conduction band and become delocalized. In a semiconductor, this gap is less. This gap is less. So what happens is that as your your electrons, if they gain enough kinetic electrical energy, that's why, remember, we talked about a threshold. There is a certain threshold. If they gain enough energy, they will be able to go from the valence band to the conduction band, and then they will be able to delocalize. So this is why a semiconductor can partially conduct electricity in certain conditions. In certain states, it can conduct electricity, and that is due to the fact that there is the gap between the valence band and the conduction band. Insulators, the gap is so huge that it is simply not overcome by electrons, and as a result, insulators do not conduct electricity. So when we talk about our semiconductor, another thing that you have to remember in a semiconductor, if you guys remember, I told you that the number of delocalized electrons is low. Remember, I told you metals have a huge number of delocalized electrons, semiconductors have low. So this is the reason. This is the reason they have less number of delocalized electrons, because the electrons have to overcome the forbidden gap. So what happens that since the number of delocalized electrons in the semiconductor are low, the current they will carry is also going to be low for the same voltage. So if I take a piece of metal and I take a piece of silicon, and the metal I'm going to go ahead and put it at 10 volts and silicon at 10 volts, the silicon has less delocalized electron. So for the same voltage, it will give me a lower current. So what happens? Now, at higher temperature, whenever you increase the temperature, what will happen? The electrons will gain kinetic energy. The electrons will gain energy, and they will be able to move from the valence band to the conduction band. As they're going to move from the valence band to the conduction band, um, what is going to end up happening? That first of all, we know that whenever temperature is going to increase, the resistance is going to increase, right? Why is the resistance going to increase? The reason your resistance is going to increase is because more collisions. That's what we talked about, that there are going to be more collisions taking place. But at the same time, there is electrons have more energy to go into the conduction zone, right? Now, both of these things happen simultaneously. There are more collisions also taking place, but at the same time, um, the number of electrons in the conduction band are also increasing. Both the things are happening. Now there's an overall effect. The overall effect, the resultant effect of both of these combining. So one is increasing the resistance, but the other thing is increasing the number of electrons. The overall effect is that as the temperature increases, the resistivity decreases. So the resistance decreases. That's the overall effect of it, right? So that is why a thermistor was acting the way it was, because it's made of a semiconductor. So the overall effect, what is happening, that the electrons are gaining more energy, they're able to go up to the conduction band. But at the same time, there are more collisions taking place. Both of these effects together, they will produce an overall resultant effect. The resultant effect is going to be that as the temperature is going to increase, the resistivity will decrease. And as a result, the resistance decreases. So that is why you're observing that relationship in a thermistor, because of the fact that it is made up of a semiconductor. Any confusion? Anybody wants to ask anything? Ridena, pass it, all clear?
Yes.
Okay. So this is the graph that you guys can see. Now, when we talk about a diode, just give me 1 second. When we talk about a diode, right? So a diode is actually made up of two different types of semiconductor, right? So there are two different types of semiconductors, not just one. So normally what happens is when you take two different types of semiconductor, it creates an energy barrier at the junction. So the junction where the two semiconductors are joining with each other, you create an energy of barrier. Sorry, I'm saying energy of barrier. I mean, you create a barrier of energy. What does this energy barrier do? This energy barrier blocks the movement of your electrons across this barrier. So this barrier will block the movement of the electrons. If a forward force is applied, a forward voltage, if a forward voltage is applied, this barrier can overcome and the electrons can go travel from one direction to another. But at a reverse direction, in the opposite direction, charged electrons are not able to overcome, or they're not able to cross the barrier, right? They're not able to cross the barrier, and they are not able to travel in the opposite direction. Now, generally speaking, this is up to a certain voltage. Diodes generally work at low voltages, right? At low voltage, you're going to go ahead and observe that at low voltage, there is no current in the reverse direction. In the forward direction, what happens is this. Even a little bit of forward voltage, even a little bit of voltage in the forward direction is enough. It's enough to allow the electrons to overcome the barrier and start traveling from negative to positive and allow the conduction of electrical current. Now, what happens in the reverse direction? This barrier cannot be overcome, but this only happens at low voltages. Once the reverse voltage becomes large enough, it can overcome this energy barrier, and it can also allow the current to travel in the opposite direction. So when I talk about this entire process, this is only when we talk about a diode, this is generally in low voltage, right? For forward conduction, this is only at a low voltage. At a higher voltage, if the backwards voltage becomes high enough, it will allow the current to travel in opposite direction as well, right? So this is how a diode is actually going to be working. Now, we have talked about light-dependent resistor and we've talked about thermistors. So light-dependent resistor, I told you, they have an inverse relationship. Greater the light intensity, lower the resistance. Lower the light intensity, greater the resistance. LDRs are also made from semiconductor material. So what happens when the light lands on the material? It provides energy for the what happens that it provides energy to the electrons. As it provides energy to the electrons are able to go from the valence band to the conduction band. So the number of delocalized electrons increase and the resistance decreases. So whenever light intensity increases, the electrons gain more energy. They're able to go from a lower energy level, that's the conduction valence band, to the conduction band. So number of delocalized electrons increase, so resistance decreases. Inverse relationship, increase in light intensity decreases the resistance. Thermistor is also made in the same way. And when we talk about a thermistor, we've talked about thermistor. They also have show you an inverse relationship They also show you an inverse relationship where they're generally going to show you that as the temperature is going to increase, the resistance is going to decrease. And we've already talked about how it's going to work. Thermistors are also made up of semiconductors. So diode, they're made up of two semiconductors that are joined together with each other. Light dependent diode and thermistor, both of them are made up of generally just one semiconductor material. Okay, when we talk about an insulator, so an insulator, the energy gap between valence band and conduction band is so large that there's simply no electrons in the conduction band. Like they're simply not able to jump from a low energy level to a high energy level. You need a really, really high amount of energy to make it happen. And the problem is that if you supply that high amount of energy, you generally need the melting point of the material, and the material either gets melted or it gets damaged before it can actually start doing conduction. It will end up getting damaged. That is why insulators are insulators. So there is a certain electrical energy you can provide that will make them conduct. But before you manage to meet that requirement, the material ends up getting damaged. That is the problem with insulators, right? So that is why insulators are not able to conduct electricity. So now we know that it's not just the entire story is not just about delocalized electrons and all of that. Now we have a good enough idea about that the entire story so far we had always studied that it's about the delocalized electrons, whether they're there or whether they're not there. Now we know the entire story about conduction band, valence band, and why metals are able to conduct electricity, and we know why semiconductors can partially conduct electricity. Now, there is also something known as superconductivity. When we talk about it, we know that resistance increases with higher temperatures. We talked about it that when the temperature is going to increase, there's going to be more kinetic energy. The electrons are going to have more collisions. When the electrons are going to have more collisions, they will slow down. So resistance increases. We have talked about this. Now, when we go ahead and we talk about it, we know the opposite is true for cooling down. If we cool down a material, if we decrease the temperature, the resistance also decreases. Now, generally what happens is that when you're cooling down a material, if there's a certain temperature limit, it's known as critical temperature. Fine. So if you cool down a material below the critical temperature, the resistance drops to zero, like instantly. There's this critical temperature, and the moment you meet that critical temperature, the resistance drops down to zero. This is known as superconductivity, right? So when we go ahead and we talked about it, this is what superconductivity is. So when we go ahead, so superconductivity is when the resistance drops down to zero when you meet a critical temperature. So the critical temperature is different for different materials. And that is it for our topic of basically our topic of electrical quantities. Is there any confusion? Does anybody want to ask anything related to the topic?
No, ma'am.
Ridhana, is this all clear?
Yes.
Okay, so this is the topic of electrical conductivity that we had to go ahead and we had to go over. This is the first part of the topic of electricity. Now the next part of the topic of electricity that we have to go over is electrical current. So in electrical current, we are going to be looking at series circuits and parallel circuits, which is something that you already have covered before, but we're also going to be looking at potential dividers and potentiometers and all of that, which will be something that I don't think you guys have done before in this much detail. So I think we'll go ahead and we'll stop it over here for today. And then in the next class, we're going to go ahead and start off with our topic of electrical current. Okay?
Okay, ma'am.
Okay.
Okay, thank you so much, guys. See you in the next class. Have a good day.
Thank you, Miss. Bye. Take care.
Bye, Ravena.